Good morning. Welcome to Krishna's classroom. We look at another application of the Hahn decomposition theorem, or another consequence of the Hahn decomposition theorem. Another consequence of the Radon-Nikodym theorem, which is something worth looking at. It generalizes, and is called the Hahn decomposition theorem. Now, the result is the generalization of the following fact. Suppose f is some be a real valued function on the interval a. Okay, then you can, so f may be positive or negative or equal to 0. Therefore, we can write mod f is greater than or equal to 0. Okay. Now you can split this function to two parts, namely the can be written as the difference of two non-negative functions. Now this is the result. So you see, you look at this function, you call f plus define as f, and f minus define as now both these functions are, this is greater than or equal to 0, this is also greater than or equal to 0. Now you can immediately verify the following, namely f plus is equal to mod f, and f plus this is equal to, okay, so I'll make a mistake, I'll take half of this. So that this is equal to this, and f plus minus f minus equal to, so f can be split into the difference of two non-negative functions. Now this is quite simple. So you take the interval 0 to 2 pi and consider the function sin x, whose graph is given here. So you take fx equal to now the fx plus mod fx is essentially given, the graph of mod fx is given by this. This is mod fx. This is f. So fx equal to sin x. Now you see that sin x plus f is what? It is going to be 2 sin x over here and 0 over here. That is, wherever the function is positive, it is going to be twice that. Therefore, we correct it by 1 by 2 and define, while defining f plus, we take half of mod f plus f, which is greater than or equal to 0. And if you look at this one, f minus as mod f minus f would be the reflection of this, and therefore it will be 0. From 0 to pi, it is going to be the 0 function, and over here it will give you this part. So you have two non-negative parts. The two non-negative parts are, so this is so you have, this is one part, this is one function, this is of course this function, this is one function, and the other function is going to be 0 over here, and then so you split it up into f plus and f minus. Okay, you take the sum of these two, you will get a split up. So this is the decomposition of the function f into the difference of two non-negative functions. Okay, so the analogous result we try to get for the measures. So this is the content of the Hahn decomposition theorem. So let us state the theorem. Let me give the statement. So here f plus equal to this is equal to 0. And in this case, f minus is equal to 0 both f plus and f minus are now non-negative functions. Okay, so that is the breakup that you have, and consequently you can write mod f as half of or sum of f plus and f minus, and f as the difference of f minus, f plus and f minus. So that's the result that you have. Okay. Now we are going to generalize this theorem. This is the Hahn decomposition theorem. So let me give the statement. Let mu be a real measure on a measurable space X. Then there exists sets A and B, measurable sets A and B belonging to the sigma algebra M such that is empty, and such that the positive and negative variations mu plus and mu minus respectively of mu B intersection E for any E belonging to M. Okay, so this is the theorem. So you can actually partition the space to A and B, where A union B equal to X. It's a disjoint partition, or it's a disjoint, the two sets are disjoint sets, so that A union B is equal to X and A intersection B is the empty set, and such that the positive and negative variations mu plus and mu minus of mu satisfy this. Now we already have stated earlier that this is the result, that is mu equal to minus, and the total variation of mu equal to minus. So this result we have already seen, and this is called the Hahn decomposition of, this is called the Hahn decomposition of this we have stated earlier, but now we shall actually prove this result, this breakup. we mark X is the disjoint union of two disjoint measurable sets A and B such that the entire positive mass A carries the positive mass and all the negative mass. Okay. Now this is because mu E is contained in A and mu E is negative if this is the breakup. Now the pair induced by mu. So this is the Hahn decomposition. What is it? That is X is equal to this is the Hahn decomposition, and this Hahn decomposition is subject to or is what is induced by particular mu on the space. Okay, right. So let us prove this theorem. The proof is not difficult. See, in our example of a function, we found that the function induces a decomposition of the interval 0 to 2 pi, to 0 to pi and pi to 2 pi. Okay, this is the A is 0 to pi and B is pi to 2 pi. So that's the Hahn decomposition that you have for that set. And it is induced, this is the one induced by a function. So if you use a different function, then it is going to be a different decomposition. So each function induces a decomposition of the space. Likewise, each real measure induces a decomposition of the whole space into A and B, where A contains the entire positive part of that measure and B contains the entire negative part of that measure. That's the split up that you have. Give the proof. Here we use the what you call radon encoding representation. Okay, by the total variation measure mu is essentially a non-negative measure. Okay, so we have this result that mu is absolutely continuous with respect to. Hence, by the radon encoding theorem, d mu h now you see that mu is a real function and hence h is a real function. It's a real value. Okay. Further, we have seen that this is the polar representation of mu, and therefore by the now this is what we have proved last time, that what do you get? Equal to 1. Mod h equal to 1. Maybe you will have to redefine it on a set of measures. 0. In fact, h is real almost everywhere on X, and by redefining as we did in the proof of the polar representation theorem on a 1 on the entire X. So since H is real, and equal to 1, H is equal to so it is either plus 1 or minus 1. Now let us define A n. Put A equal to the set of all X and B as minus 1. So it splits into two sets. It's plus 1 or minus 1. Mu plus equal to now you try to give a representation for this. So what is that going to be? So since equal to H on A and 0 on B, because H is equal to 1 or 1 is the value of H on A is equal to 1. Therefore, this is equal to, you get 2H and half of 2H is H on A, and this is equal to 0 on B. That's easy to see. Any E belonging to M this is the representation theorem. Half of that you write this one. This can be, the representation theorem is actually half of, this one corresponds to 1 and this one corresponds to H. It comes from that actually, this representation. And that is equal to integral over intersection over A E intersection A. Now you get the representations. Now you see that A union B is equal to X. Now mu E is actually equal to mu of E intersection A plus mu of intersection B. Because A union B is equal to X. Okay, it comes from that. Minus mu of E intersection B equal to this comes from star, and what you have is for mu E you have mu E equal to mu plus E minus mu minus E. Okay, and therefore mu minus E is equal to mu plus E minus mu E, and this is equal to mu of mu E, and that's equal to mu of minus, you split it up, and this comes out as mu of and that turns out to be simply minus, and these two cancel out, mu of therefore mu plus E is equal to mu of E intersection B, and mu minus E equal to minus of mu B intersection, and you can get all these results that you have mu plus comes out. So this is what is called the Hahn decomposition. So the Hahn decomposition is essentially the breakup of X into the set A and the set. Now we show in our next result that this is in some sense an optimal decomposition. Okay, an optimal decomposition. I'll go back to explain this out. I go back to the example that I have considered, the function. Now you see that if you consider the function, so that completes the proof. So let us 2, 5. Now here, see, you have two breakup. A turns out to be simply, B turns out to be 5 to 2. Okay, so this is the breakup that you have. And now you know, since I am redefining the function at 0, at pi the function becomes 0, there I redefine the corresponding function to be okay, so that point is included this one, therefore I get A. So this is equal to okay. Now you see this. So one breakup I have is I can write it as F plus. F I can write as F plus minus F minus. This is the breakup that I have. Now I can also do the following. What I can do is I can write this as F plus plus 1 minus plus 1. This 1 cancels. Okay. And then what happens? Suppose I call this G and H. Suppose I call this, then F is equal to G minus, where both G and H are positive functions. So this is another way of writing it up, right? But what you have is this, the following is true, that F plus is less than or equal to G and equal to H. So this is probably the optimal in the sense that no smaller function, no function which is less than F plus and F minus would give you the particular breakup that you have. So we will have the corresponding result here. Okay, so that's why I said it is somewhat optimal. It's an optimal breakup that you get for the function F. Correspondingly, you have for mu the breakup mu plus and mu minus, and mu plus is optimal and mu minus are also optimal. So we will write it up this. Breakup. So we write the corollary. If mu equal to lambda 1 minus lambda 2, where both lambda 1 and lambda 2 positive integers, then lambda 1 is greater than or equal to mu plus and lambda 2 minus. So this if mu is another breakup, has another breakup as lambda 1 minus lambda 2, where both lambda 1 and lambda 2 are positive measures, then it implies lambda 1 is greater than or equal to mu plus and lambda 2 is greater than or equal to mu minus. So something smaller than mu plus, with that you cannot break up. So this is a sort of optimal breakup that you can have. So we will just give the proof of this. Now breakup and gives the Jordan decomposition So you have mu is the real measure. So mu plus total measure of mu plus mu this is the optimal breakup that you have. And the consequence is that this will give you, this will break up mu into the difference of two non-negative, two positive measures, namely minus minus. So let us prove this corollary or give the proof corollary. Suppose mu is lambda 1, then we have mu plus e because given mu we have a and b set as a Hahn decomposition, and this is of course less than or equal to lambda 1 is of course mu plus is less than or equal to lambda 1, therefore this is lambda 1 e intersection a, and this is lambda 1. Now further you have mu plus mu minus equal to lambda 2. This is given. Therefore, mu plus minus lambda 1 equal to mu minus lambda 2. Mu minus lambda 2. So lambda 1 mu plus is less than or equal to lambda 1 means this is negative, so lambda 1 minus mu plus is positive. So the consequence of this is that less than or equal to 0 implies equal to 0, which in turn implies that minus is less than or equal to lambda 2. Okay, and so this is an optimal breakup that you get. Okay. So we conclude today's lecture with this, and now from the next lecture we will take up what are called a bounded linear functions. So thank you very much.